Hi, Algebra 2 Honors. This is Unit 12, Day 3. Today we're taking a look at some log bases, and we're going to get into the domain of log functions. Now, we know a little bit about what log graphs look like from Day 1, but we're going to extend that concept a little bit further today. Before we get there, I have two equations at the very top that have some logs in them, and I want to talk about some processes of how we would solve these equations. If you look at number 1, we have a single logarithm on the left side and an equals 3 on the right side. The main idea here would be that if you have a single log, in order to solve that equation, let's convert it to exponential form, right? This is currently Benny base number exponent. We can convert this to exponential by saying that x squared minus 22 would equal 3 to the third power. Now, there's less of a chance we'll make a mistake here because this base and this number match. But keep in mind that it's the base raised to this number. That's what goes on this side right here, in case those are ever different. All right, so now that I had this in exponential form, let's keep going. We get x squared minus 22 is equal to 3 cubed, which is 27. Add the 22 to the other side. X squared is now equal to 49. You really had two options. You could bring the 27 over here and factor. You can add the 22 over here and then square root, square root. Now, don't forget that if you take the square root of both sides, we do need to consider that it's plus or minus 7 as our two solutions. So log equations, as soon as we convert to exponential form, can be pretty easy to work with. The one thing I'll caution you about with number 2 is that we can't convert to exponential form right away. So if you have multiple logs that are being added or subtracted or anything of that form, you must condense the logs into a single log first, just like I had in number 1. Well, it's a good thing we know some really good skills of how to condense logs. We know that when we condense addition, that the property is that these would condense to multiplication. So the very first step, we're going to write this as log base 3 of x times x minus 2. That would be the condensed form of the addition that we started with. So now at this stage, it looks pretty much like the last one, right? We have log base 3 of a quantity equals 1. Let's convert it to exponential form. The other thing I'm going to do is I'm going to distribute that x in here to get x squared minus 2x. What would be on the other side? 3 raised to the first power. Okay, so make sure the base of the log gets raised to this exponent on this side. Now 3 to the first is just 3, and this is a more traditional factoring question. You will have to subtract 3 over to this side, set it equal to 0, and then use the add multiply rule. So that's going to be x minus 3 times x plus 1. And we get two solutions in the end, x equals 3 and x equals negative 1. However, just like with other equations we've solved this year, 3 is a solution, negative 1 is not. Does it mean that we always cancel out negative solutions? The answer is no, because negative 7 actually does work here. So why doesn't negative 1 work on this side? Well, if I plug it in, maybe just even to that first piece, log base 3 of x. Log base 3 of negative 1, why does that have no solution? Because it's like saying that 3 to some power will equal negative 1. And we know that that's never going to be true. Even if I pick a really large negative power, 3 to a negative just turns into a fraction that's positive. So there's never an input for x here that's going to make the output negative 1. Therefore, log base 3 of negative 1 has no value. So you want to make sure that when you get your answers, you go back and check in the original equation, make sure that there's no restrictions. And this will make more sense when we get to our domain part of the lesson, but this is kind of a good start there into thinking about some domain issues. Okay. All right, let's move on to talk about log bases. So what I want you to consider here is the exponential equation, 3 to the x equals 32. I'm going to show you kind of two different approaches of how we can solve this. Okay, so for option 1, we're just going to take the log of both sides. So when I take the log of both sides, what I'm talking about is that I'm taking log base 10 of both sides. So I'd write this as log of 3 to the x equals log of 32. Why does taking the log of both sides help me to solve an equation like this? Well, think back to your log properties. We have the Angry Birds rule, don't we? So we're going to slingshot that x back and shoot it right to the front there. So this becomes x times the log of 3 equals on this side log 32. And then really quickly we can get x alone by dividing both sides by log 3. So x is equal to log 32 divided by log of 3. All right, so that is one way to write the solution to number 1 here. Option 2 would be to take not just log, but why don't I choose the base of the log to match the base of that exponential? Take log base 3 of both sides. And we'll see how the solution actually goes a little bit faster. If I choose the base of the log to match the base of this exponent right here, then log base 3 of 3 to the x, if you go back to day 1 of our notes, we said that when the base of the log and the base of the exponential match, we just get x. So log base 3 of 3 to some power is just the power there. So x equals log base 3 of 32. And because I'm telling you that these are equivalent techniques, that they're both valid, that means that these answers are equivalent to one another. Okay, so then why wouldn't I always choose option 2? Well, what if I said, well, I want my answer rounded to the nearest hundredth? Okay, so this is an exact answer right now in terms of these logs. But to the nearest hundredth, the issue is when I go to my calculator, I don't see log base 3 anywhere. I see log, but how do I make that base 3 pop up so I can type this into the calculator? Well, not quite there yet into showing you how that works, but we have this equivalent option. So log of 32 divided by log of 3 is 3.15 to the hundredths place. Okay. And that kind of makes sense to me because 3 cubed would be 27. 3 to the 4th is way too big. That's 81. So I knew that the answer should be somewhere between 3 and 4. Okay, so what this brings us to, though, is something called the change of base rule, or the change of base formula. And what the change of base formula does for us is it can take something where we have log base 3 of 32 and convert it into common logs. This way we can more easily evaluate and type that into the calculator. Okay. So in general, for the change of base rule, if you have log base b of x, that's equivalent to log of x divided by log of b. So it's log of the quantity on the inside divided by log of the base. Now, it doesn't just work for base 10, which is pretty cool. It would work for log of any base. You could actually write it as ln of x over the ln of the base. You could choose whatever base you want. You could do log base a of x over log base a of b. Any of those patterns would work such that you would get the equivalent expression there. Okay. So let me just prove to you that if I had used natural logs to solve instead of using log base 3 or log base 10, that if I do the natural log of 32 divided by the natural log of 3, we wind up getting the same answer of 3.15. Okay, so change of base, because log properties hold true no matter what the base is that we're using, they're going to work the same in terms of getting the same results. So therefore, if I asked you, well, hey, what's log base 2 of 7 to the nearest hundredth, let's say? So what is log base 2 of 7? It's pretty close to 3 because log base 2 of 8 would be 3. But to type that in, we could do log of 7 divided by log of 2. You could do ln of 7 over ln 2. It's really up to you. All right, so log 7 divided by log 2 is 2.81 to the hundredths place. Okay. Maybe just one more. Let's do log base 4 of 32. Okay. This is one where I might get a little sneaky on you here and say, all right, let's not use common logs. If you look at the number 4 and you look at the number 32, maybe in your mind they both have a connection to having a base 2 connection there. So what if I wrote this as log base 2 of 32 over log base 2 of 4? Because like I said, you can change it to whatever base you want. And if I change it in this format, it's easier for me to see that, oh, 2 to the 5th power is 32, and 2 to the 2nd power is 4. So therefore, log base 4 of 32 is 5 halves. Well, the calculator better tell me the same thing. Log 32 divided by log 4, is that 5 halves? Sure is. Is the natural log of 32 divided by the natural log of 4 also the same thing? Yes. So if you wanted to try a little bit on your own without the calculator, this one has a nice exact value, whereas log base 2 of 7, we're not going to get very far in terms of getting a nice answer to pop out of that. Okay. All right. Last thing we're going to talk about today is some domain of log functions. And in order to get you to recall domain, let's see if we can remember what the graph of log base b of x looks like, where the base in question is bigger than 1. Okay. Now, if I'm being honest, actually, the base doesn't really matter in terms of finding domain, but the graph that I'm about to show you is for a base that's larger than 1. Okay. Log base b of x, what does that look like if this is a base 2, 3, 4, 5, or so on? It has a vertical asymptote right on top of the y-axis at x equals 0. It has an x-intercept at 1, 0, and has a general curve that looks something like this. So if I said, well, what happens when I graph this function, log base b of x minus 3, hopefully you remember that according to transformations, when you change the inside of the equation like this, that's going to be a horizontal shift. In fact, it's going to go in the opposite direction of that minus 3. It's going to move 3 to the right. So what happens is when I move this 3 to the right, the vertical asymptote moves to x equals 3. The new x-intercept is at positive 4, and you get a graph that looks something like this. So what I want to talk about underneath these two graphs is what are the domains for each of these? The domain of the first graph is from 0 to infinity, right? There's nothing on the negative side of the x-axis. We can't include 0 where that asymptote is. Similarly, wherever the asymptote is at x equals 3 in this case, from 3 to infinity, that's the domain of this graph. So what I want to know is, in general, how could I have gotten that information just from looking at maybe the quantity on the inside here? How can I determine domain just by looking at what's on the inside? So in general, like we mentioned earlier, we cannot take the log of something that is negative. Nothing to a power will ever give you a negative number that's on the inside here. So in general, if you have log base b of some quantity, I'm going to put that quantity, I'm going to represent it by a box. To find domain, what we do is we take whatever's in the box and we set it to be greater than 0. Okay, if we want to ensure that it's always positive. By the way, you can't get 0 either. Okay, we don't want a 0 in here. That would also not exist. In general, for log domain, take whatever is inside the box, set it to be greater than 0, and you are good to go. Let's see if we can apply that to some specific cases here. So the first one is, let's do the domain for log base 2 of 3 minus 4x. Okay. If I ask you, without even graphing it, what does the domain of this function look like? It's going to be take 3 minus 4x, set it to be greater than 0. I like keeping x on the left side always. That could be personal preference, but maybe you'd agree with me as well. Subtract the 3 over, and when you divide the negative 4 from both sides, make sure you flip that inequality. This gives you that x is less than 3/4. So if x has to be smaller than 3/4, the domain and interval notation, which is how I'd like you to write these, because I think it's the most concise way, is that the domain would be negative infinity to 3/4. Okay. And that's pretty much it each and every single time. And it doesn't matter what the log base is. Okay. It's independent of the log base. We can do this no matter what. All right, next one is log of x squared minus 4. So if I gave you y equals log x squared minus 4, and I ask you to find domain, we're going to now set x squared minus 4 to be greater than 0. Hey, by the way, if I don't write a log base there, what base is it? It's definitely base 10. Okay, it's usually not written, but know that that's base 10. How do I solve x squared minus 4 is greater than 0? This is a quadratic. So when you have a quadratic on the inside, before it was linear, you have to partition if you go back to quadratic inequalities way back when, probably in like unit 7 or something like that. Okay, so in order to partition, you need to find the solutions. When does this equal 0? Well, you can quickly factor x plus 2 and x minus 2. And what that tells you is that the solutions when this equals 0 are at -2 and +2. Now, I'll tell you, for log domains, we're never going to include those. We don't want to include the zeros because we don't have that equal to piece. Okay, but now you're just going to test values. If I test -3, -3 plus 2 is negative. -3 minus 2 is negative. Is this sounding familiar, maybe? I hope. All right, so that altogether is positive then. If I test 0, 0 plus 2 is positive. 0 minus 2 is negative. A positive times a negative is negative. And then lastly, if I test 3, you will get positive out here, which 2 positives multiply to give you a positive. What am I looking for? If I'm looking for greater than 0, I want positives, don't I? So wherever you get positive on the number line, that's what we're going to shade in. And therefore, your final solution to the domain here is that the domain would be -infinity to -2, parentheses, union 2 to infinity. Okay. So just a little bit of partitioning thrown in the mix there. Let's do one more just to make sure we're really good with the partitioning part here. We'll do y equals the natural log of x squared minus 5x and then -6. Okay. So for this last one here, again, natural log, it's the same idea as log base 10. It's just log base e. Okay, so you're going to set the inside x squared minus 5x minus 6 to be greater than 0. We've got to factor that. Be careful because you have to really watch the signs here. 2 and 3 can multiply to 6 and add to 5, and 6 and 1 can kind of do the same thing. You just got to pay attention closely to those signs to make sure that you have this factored correctly. If this has to be a -6 and the middle is -5, it's going to factor into x minus 6 and x plus 1. Okay, those will multiply to -6 and then add to -5. So the solutions you're partitioning around here are -1 and 6, open circles on both. Okay. If I test -2, -2 minus 6 is negative, -2 plus 1 is negative. 2 negatives multiplied is a positive. You're going to see a really similar pattern here, but 0, you get negative times positive, which is negative. Plug in 7, you get positive. Okay. So hopefully that wasn't too fast. If you have questions about the partitioning process, please let me know next time we are in class. But I'm looking for positive pretty much always. Okay. I always want this to be greater than 0. Therefore, the domain is -infinity to -1, union 6 to infinity. Okay. So we got through a lot today. There was a lot of good stuff with changing that base if needed, so we can type in rounds in the calculator. There's some really good information about domain here and a little bit with log graphing. So we even did some solving equations at the beginning. If you have questions about any of this, please let me know next time I see you. Have a great rest of your day.